Hello, please join me in this video where I am going to discuss some of the strategies involved in solving a multi-step synthesis problem. For example, let us consider the alcohol on the left as our starting material and the one on the right as our product. So before we start solving this problem, we need to visualize and compare your starting material with that of the product. So in this case, you could ask yourself questions like, is there any change in the number of carbon atoms? Is there any change in the functional group? Is there any change in the position of the carbon holding the functional group? Okay? So let us consider the number of carbons in this case, 1, 2, 3, 4, 5. And in the product, we have 1, 2, 3, 4, 5. So there is no change in the number of carbon atoms. But we can now clearly see that in our starting material, the hydroxyl group is at position 2, while in our product, the hydroxyl group is at position 3. Position 3 seems to be more substituted than position 2. So the hydroxyl group has moved to a more substituted carbon. Now, in our previous chapters, we learned how to install a hydroxyl group in a more substituted position if we have an alkene. Okay? So if we can generate an alkene between carbon number 2 and 3, then that can help us to direct the synthesis of our product. And to form an alkene from our starting material, hydroxyl group is not a good leaving group, so the first thing we need to do is to transform it into a good leaving group. We can do that using tosyl chloride with pyridine to install a chloride group. And then we can use sodium ethanoate to do an E2 reaction, which gives us the Z-safe product, that is the more substituted alkene. And then we can do an acid catalyzed hydration to form the product that is desired. Or we can use oxymercuration demercuration, which uses mercury acetate together with water, followed by sodium borohydride. Okay? And we can play around with synthesis that involve multi-step strategies. For example, assuming we are moving from this starting material and we wanted to go to the one on the right at the bottom. So that means we want to install the hydroxyl group in a different position. In this case, it is going to carbon number 1 as opposed to 3. So the way we can do that is to transform again the alcohol into a good leaving group, then kick it out, but in this case we are going to use a bulky base. If we use a bulky base, we are going to do Hofmann elimination and end up with a product that is less substituted. Okay? Once we form the less substituted product, then we can use hydroboration oxidation to install the hydroxyl group in the less substituted position. So what you realize from here is that you need to know the reagents necessary to perform one-step synthesis. For example, you need to have the materials necessary to perform substitution and elimination reactions at your fingertips. For example, whether you're going to do as SN2, SN1, E2, or E1. You need to know the reagents necessary to perform alkene addition reactions, whether it is a one-step or a two-step synthesis. You need to know the materials necessary to perform alkyne reactions, the ones involving either one or two-step synthesis. You also need to know how to alter the carbon skeleton. For example, if you have an alkene, we can do an oxidative cleavage if we use ozonolysis, that is involving ozone and dimethyl sulfoxide. If we have an alkyne, you need to know how we can do an oxidative cleavage to form carboxylic acid, that is by using ozone followed by water. If you want to be able to extend the chain, then we need a terminal alkyne, that is an alkyne that has a hydrogen at the end. Then we can use a base such as sodium amide to be able to form a deprotonated alkyne, and then we can use this as a nucleophile to be able to attack an electrophile to form the product of choice. Another strategy you can use to form a new carbon-carbon bond is by employing sodium cyanide, which we said acts as a good nucleophile. So you can end up extending the chain by one carbon, but then you're also going to have a nitrogen attached to the compound. You also need to know the reagents required to perform radical reactions and have them at your fingertips. Okay? So, with the multi-step synthesis, we can move in the forward direction, like we can have an alkyne, transform it into an alkene, and finally to an alkane. So this involves 2 steps. We can go backward. Here we have an alkane that we can transform into an alkene and then into an alkyne. And that brings us to what is called retrosynthetic analysis. In retrosynthetic analysis, we start with our final product and work our way backwards, okay, until we reach where the starting material is. So if we start with our alkyne, then we should think of how can we make an alkyne. From what we have learned in the previous chapters, we can make an alkyne from a dihalide. The dihalide could be vicinal or it could be geminal, where the halide groups are on the same carbon atom. Okay? Then the next thing we should be asking is, how can we make the dihalide? We can make a dihalide if we have an alkene. Okay? And then the next thing we should be asking again is, how can we make an alkene? We can make an alkene if we have this alcohol and transform it into a good leaving group, and then we use a base that will help us to make an alkene. So now we need to figure out how to put everything together, right? So we know that we can make the alkyne from the dihalide. All we need is a base and then with water, okay? Because we said when you form this product, it's going to be a terminal alkyne. That terminal alkyne, the pKa is around 25. So we need water to be able to protonate the terminal alkyne and also to protonate the base that we are using. The dihalide, we can form it from an alkene. And the way we achieve that is to perform halogenation. Okay? To form an alkene from an alcohol, we can transform the hydroxyl group into a good leaving group using tosyl chloride and pyridine, and then we can use a base that is going to help form the alkene. Okay? So the reaction involves the use of the alcohol, then from the alcohol we transform it into a good leaving group, and then we do elimination to give us the product, and then we do halogenation, and then finally we install the alkyne. thank you for watching, and please take a look at the examples I have provided in the lecture notes and let me know if you have any questions. Have a good one.